What I will do is really give an high flyover overview of our project and discuss a little bit some recent results in more detail. So the philosophy of HiBrain is to combine both photonic and electronic platforms for edge inference, for neuromorphic computing at the edge. And the project started in 22, and we still have till next year, October. So we got a half-year extension to continue, and we have a kind of sharp goals for both energy efficiency and for latency. The philosophy to combine these two platforms is that we would like to use photonics, integrated photonics, really for low latency and high throughput pre-processing, first stage, especially for CNNs. That's where the critical bottleneck lies, and then go into electronics when we need more like fully connected networks. And then we have this kind of funny component from us in Twente, what we call reconfigurable nonlinear processing units, where we try to do material-based nonlinear processing. I'll come to that in a moment. So this is how we envisioned it at the start of the project. So really initial convolution layers have a lot of linear processing going on, and then going into potentially non-linear layers. You will see actually that over time we started to kind of move around these blocks and really looking at the actual application where it would make sense to either first start with non-linear and then move to linear. So the objectives are as follows. So we have this PCP, the photonic convolution processor, as work of the group in Münster, Heidelberg, the group of Wolfram Pernice, also the group of Harish Bhaskaran in Oxford, Nick Pharmakidis, working really on this photonic platform. Then we would like to interface that with the AIMC, the Analog in Memory Computing of IBM Research Europe, the group of Abu Sebastian. And then finally also we would see if it makes sense to have all three platforms together, so including also these nonlinear processing units of Twente. And then finally see if we can indeed demonstrate this low latency and energy efficient applications. So here you see the partners in crime. So the project's coordinated from Twente, Harish, Oxford, and we also have Trust IT dissemination partners. So all these very beautiful slides and logos and stuff that is really owing to their contribution. I already mentioned Wolfram at the start of the project, still in Münster, and moved now most of the group to Heidelberg. IBM Zurich, IBM Research Europe with Abu Sebastian and Ngazi Siet. Right, so as I said, we started in 22, kickoff in Twente. We have our yearly in-person meeting, so this was in Heidelberg. This was last year. There are some participants here also who were in this beautiful place, Erice. And actually just 2 days ago, before coming to this meeting, we had again an in-person meeting at IBM Research in Rüschlikon. So as I said, there's just about 1 year to go, and then we'll close up the program. So we have nice video if you're interested on YouTube. But what I'll do is go through the respective work packages. So the first one, or the work package 2, the first, let's take technical work packages, focuses on these photonic convolution processes, the integrated photonics. And here is really the idea that you realize these photonic or these crossbar arrays that you have seen earlier today in the context of electronics, so where you can very nicely make use of Ohm's law and Kirchhoff's law to do a matrix vector multiplication for you, to bring that to the optics domain, where you have to come up with other tricks actually to do multiplication and addition. So addition is basically normally realized by adding up intensities of the light, and multiplication is then also a matter of trying to modulate the intensity or the phase of light. So very often what you do is you play with the evanescent field on the waveguide to modulate the intensity of the light. So these are kind of standard building blocks. Now, if you bring them together in a crossbar, which at first glance looks very much like the electronic one, then you can combine these two elements. So you can do the multiplication here by the modulation of the light, and basically adding up then the intensities of all lights, and there you get your matrix vector multiplication in light. The reason why this is a priori interesting to do that in light instead of electronics is because of the speed, the enormous high bandwidth that in principle you have. You can multiplex in wavelengths. You can, in the gigahertz regime, modulate your electronics or your photonic signals. So you can in principle be extremely fast and high bandwidth. So if you are working with large kernels and this high bandwidth is critical, then optics is a very interesting option. So this is an example of Wolfram's group, what it could look in reality. So this is just a 16 by 16 crossbar where you see both these multiplication and addition elements. So over the project, there has been quite some progress in getting this now into a kind of 19-inch rack, all combined system. In this case, there is some fiber optics that goes to the chip, and here you see an example where electronic data preparation, also part of the backpropagation, is taken care of by electronics, FPGA to be precise, but where the MVMs, the bulk of the MVM work happens in the optical domain. So there's still a lot of things offloaded here to the FPGA, but this combined system gives you then very decent results on benchmark tasks like MNIST or Cypher 10. So this shows already that you can really integrate this, and the fact that you can also manipulate in the electronics domain opens up the way to also interface with the other electronics platforms in our project. It's not so trivial to really fabricate these photonic chips to the perfection that all these operations work nicely. So what you often like to do is to do some post-processing to get the properties of the waveguides right. And in Wolfram's group and also in the group of Harish, now there are kind of post-processing methods where you use high energetic ion beams, or you use kind of electron beam induced deposition of carbon, for example, to tweak the waveguide properties so that you can really get them aligned and get the operations as you design them. So here you see a couple of recent publications that refer to this integrated photonics work. Right, then I'll move on to the team at Zurich at IBM that focuses on the linear classifier. So this is based on analog in-memory computing. You have seen Damien has given a talk this morning where he explained the idea in terms of resistive RAM, memristors. In this case, the memristive material is phase change material. So it's a material that can go through a amorphous to crystalline or a reverse transition by Joule heating, which can be induced optically and electrically. And basically the workhorse for the IBM team is the Hermes project chip. The work of Ambrogio was mentioned earlier. That's the US team, but the European team works with this Hermes chip, which is basically a chip where you have many of these PCM phase change material cores connected. It's not just the phase change material. You see there is quite some periphery also around it, and there has been a lot of work put in optimizing, especially the interfacing with the actual crossbar, the PCM, and the surrounding electronics. So there is work on the analog to digital converters, which are crucial. There is work on also near memory, so local digital processing units that you would like to have, and also algorithms that basically distribute the task over one or more of these cores on the Hermes chip. Here you see actually an actual picture of the device. This actually earlier this week I could actually see what the thing looks. It's really like a big pizza. So it's a real big printed circuit board where you have all these periphery, which of course finally should be kind of condensed in maybe an application specific IC. Yeah, here again you see a couple of improvements in programming the weights of these PCM units. So really doing training that is hardware aware. Was already mentioned earlier. If you set the weights, in practice, you give a certain sequence to program the weight. In practice, you actually have to verify, and you have to come up with smart algorithms to get the weights right. So you have to verify actually also the weights, input, output, and the work here is referring to the combination of this AIMC system, this Hermes chip, with our reconfigurable nonlinear processing units. I'll come to that in a moment. There is now a work undergoing to again work into this integration of the different platforms. So as I said, we would like to get to real hybrid electronic-photonic systems. So what is going on right now is to work on these photonic-aware neural architectures, so that already in the design and the algorithms for the AIMC, for the electronic chips, you take into account the boundary conditions and the limitations also of the photonic chip. All right, so now I come a little bit closer to home, closer to Twente, where we work on this nonlinear classifier. This is actually a quite new concept. It's a device concept that we came up a bit more than 5 years ago. And the idea is as follows. It's a silicon-based device. You can see it as a kind of funny transistor, multi-lag transistor, where we can define some of these electrodes as inputs, some we can define one or more as output, and the rest of the electrodes we use as controls. It's a lowly doped device, or we fabricate it such that the active region is actually shallowly doped, typical doping concentration maybe 10 to the 17th cubic centimeter, which makes that the transport is far from trivial. We are in the process of still really finding out what all kind of mechanisms are going on there. But the bottom line is that it is very nonlinear, and it is a tunable nonlinearity. So here you see just a set of IV curves, but by playing around with the electrodes, you can get all kind of IV shapes, including negative differential resistance. So you can really kind of see it as a small physical neural network, if you like, that that you can program, that you can teach, that you can actually go through a kind of machine learning kind of learning mechanism to carry out simple neural network operations. So earlier today you heard about this evolutionary approach for finding the meta parameters of neural networks. We use quite similar evolutionary algorithms to optimize the input-output characteristics of these devices. So this is a cartoon of the device. So we define some inputs here. We have an output defined. These are now the controls. So for example, if you want to do MNIST or a part of MNIST, you play around with these electrodes. You kind of mold this electropotential landscape in a way that your input-output characteristics does something useful for your overall algorithm. So with a single device, we cannot solve MNIST, but if we build it in, if we use multiple devices, if we make a kind of network of these devices, we can really increase the computational complexity and do this nonlinear function approximation for MNIST or for doing Boolean logic or feature extraction, for example. So this is the whole idea, and this is really an accelerator for nonlinear things. So basically, till now, you have heard a lot of speeding up linear operations, which also makes a lot of sense because the bulk of neural network operations is linear. But to a point, it's also because this is the way how we look at it. We have designed our solver such that we put the bulk of the workload on linear because linear algebra is so nice. But at the end of the day, neural networks are nonlinear functions. So maybe if you take another star point, you can also put quite a lot of more weight on nonlinear computing primitives. So that's what we're actually also looking at. Right. So this is very recent work that came out just 1 week ago, exactly, which is a collaboration between IBM Research Europe and us in Twente, and actually also with Toyota Motor Europe, where we have combined now 2 of these platforms of HiBrain, the nonlinear preprocessing and the AIMC classification to solve speech recognition tasks. So to be specific, we did this for 2 independent benchmark tasks, TI-46 and also the Google Speech Commands keyword spotting task. So the first step is the feature extraction step, where we use our RMPUs, so these reconfigurable non-linear processing units. We use them now in the time domain, and also have to stress that we work at room temperature. So we have changed the recipe such that we can operate these devices at room temperature, which is of course very handy. And what we do now is that we use a circuit where we can really now take advantage of the recurrency of this circuit. So we have a very nonlinear tunable first component. Because we read out voltage, we automatically get an RC time involved, and by tuning these electrodes, we can actually tune the time response of the device. So you could say, well, you have just built a filter. In a way, yes, but it's a very weird filter because depending on the settings of the device, we can really change the spectrum fingerprint of the output. So we can turn on the higher harmonics. We can get a really a wild family of distortions and the like. And it is really also a kind of recurrent short-term memory in the sense that if we apply twice the same pulse, the response in time domain will be different. So within a certain window, this has this shorter memory, but it's tunable, and it's now a first step in the overall speech recognition task, where we don't add any pre-processing like MFCC, or we don't do any Fourier analysis. So this is really what the pre-processing is. And there was a question also earlier today, do you need any pre-processing? In this case, the analog signal from a microphone like this, for example, goes as a time-dependent voltage in analog in this device. So we don't need to do domain conversion to digital. We don't need to do domain conversion to frequency. So no Fourier or and further fingerprinting basically of the signal. So that's already an energy efficiency, an important step we take. So how many minutes do I have left? 5 minutes left. Okay, great. So what you see here is, again, this t-SNE. So this is a kind of statistical representation now of the input data set, which in this case is spoken digits. So it's TI-46, where you have different individuals saying digits, 9, 7, 3, 2, and so on. So the original raw data set you see is very much scattered. And this time domain sound bytes go through our device. So it's just one input, one output, and then a certain configuration of the controls. And then we get out in the time domain these traces, which is actually already downsampled. But if you take the t-SNE of that, you already see that there is some kind of pre-clustering going on. Definitely not perfect. So we do this a couple of times, 32 or 64 channels like these. And these are then the input to the classifier, which is encoded in the Hermes chip of IBM. Very busy slide, but just a few takeaways. What you see here in the blue bars is basically combining our pre-processing with software-based CNNs. So this is the classifier model just encoded in software. And you see that there is really a big difference if you skip this pre-processing with the RMPUs. Moreover, if we now move the software model basically to the memristors, so to the AIMC chip, we have some degradation in the accuracy, about 2% point or so, but still we have very decent overall accuracy, both for TI-46 and also for Google Speech Commands. And here now really the bulk of the work is done in analog, and the speech recognition is happening in basically physics-enabled chips. And so on our side, it's for this nonlinearity, and in the case of the AIMC chips, it's the idea of using the memristors for doing your calculation. So so why is this interesting potentially? Well, we already see that in real time. So we have for feature extraction really sub-millisecond latency. We do this with 10 times less energy compared to state-of-the-art digital solutions. So basically having similar software models loaded on digital. But the interesting thing is that we also make the job for the classifier much lighter. And so we save a couple of million parameters in training, basically, for the classifier. Whereas we have ISO accuracy for these benchmark tasks. So that's really a nice and promising result. I mean, not perfect, obviously, but gives really kind of the idea why it may be interesting to have this exploitation of physics-based system to do these edge computing tasks. And of course, we benchmarked for speech, but in principle, this is for any time-dependent task where you can match the typical timescales of your problem. So we're also looking now at video, or you can look at ECG, EEG, or what not. Okay, I don't have much time left, so I'll be very quick about further integration actions. There's really great work going on here on these photonic architectures, work of the Oxford team, also together with Heidelberg, to also make the switching of the weights in the photonic circuits much more energy efficient. So they are also now kind of world champion in low energy switching of these elements. So much more energy efficient than using heaters, for example, to change these weights. Okay, this is just from yesterday. So this was about our dissemination policy. This is a kind of the Dutch Le Monde, of the New York Times, if you like, but a little bit modest, I would say, but the Volkskrant, Le Journal du Peuple, I guess this translates, about our work. But as you can see, it has been quite a prolific project also in terms of outputs, some patents, and also we have these key exploitable results, which are also part of the whole EIC trajectory. This is maybe some of you remember very well. Isabel was also there last year, May, I believe. Yes, some of you in Erice. We have started Brainspiration, which again, the next episode will be next year, organized by our colleagues in Nijmegen at Radboud. So this is also a tradition we started last year in Groningen. We have all kind of outreach activities. This is me, for example, at a Crosser Festival with kind of headbangers try to explain the glory of physics and the neuromorphics. It's very nice. You can visit our homepage, all kind of social media things. I'll do this very quickly. With that, I would like to thank you for your attention. I'm happy to take questions.
Okay, I'll just speak up.
Yeah.
Is that okay?
Yeah, sure.
Okay. So I have my questions about the crossbar arrays, right? You've got the photonic crossbars and you've got the electronic crossbars. And you mentioned that the photonic ones have really high bandwidth, but I imagine the electronic ones also have some advantages. And then I was curious to hear you talk a bit more about the benefits of doing the hybrid thing, right? Do the advantages of these two distinct systems sort of synergize and give you some?
Yeah, very good point. Yeah. So indeed, so the strong point of the photonic crossbars, I stressed indeed speed, low latency. For the electronics, it's really the integration and the high density. So if you want to if you need fully connected layers, if you really need a high density of weights, it's basically very mundane. The fact that in photonics you have your wavelength limitation, you cannot squeeze it too much. So integration-wise, electronics is much better. Plus all the, let's say, still periphery that you would like to use. So there you could combine the best of both worlds, where it's critical to get timescales right and also the interfacing as energy efficient as possible, because otherwise, you throw away the baby with the bathwater, as we say in Dutch. Then you have all this nice technology, but the end-to-end efficiency is not great.
So my question was related to that, actually. So it's been a while, but I used to write about wavelength division multiplexing, and I can't see how you're going to exploit that if you don't have weights that can be separately programmed for different wavelengths on one device. Maybe you can do that, but maybe you can elaborate on that.
Yeah, so what people are working on is indeed using these comms and then split in different wavelengths. So you can really then spatially separate the light in different wavelengths, and then have the operations, the weights working on these respective different wavelengths. And this is about where my knowledge ends with regards to photonics, but I think that's the way how they envision it so you have one incoming light, but you can kind of fan it out and then do all these operations, and you get back. So I think that's really where you can have.
But then you've got all the disadvantages of the huge amount of real estate you need to deal with all of these different wavelengths separately. But if you could do it compactly, if you can have a material that you can program separately to deal with each of those different frequencies, right? Which, like spectral hole burning or something like that, then maybe. But otherwise, because I've looked at some of these photonic systems before, and that's where they start to fall down.
Yeah.
They work for one wavelength, but then when you really try to do WGM, they...
Yeah, no, definitely challenging, but I think in terms of the speed of modulation of light and really the bandwidth that you have, it's very hard to do that with electronics. So you have to go to application where that is critical. If not, then it doesn't make sense. So you're absolutely right. You really have to look at the application. Is my latency, my throughput, is that really the bottleneck? Then maybe it's worth all this real estate. I think that would be the answer. Yeah.
Thank you very much, Wilfred, for impressive talk. I'm always enjoying your talk. Actually, my question is regarding the algorithms that is suitable for your reconfigurable, let's say, nonlinear processing unit. Which kind of algorithms you can, let's say, implement on that? Because I have seen you use the convolutional neural network. I'm working on different algorithms. So one of the things that we developed recently is a light version of transformers, which is suitable for those kind of things. And I was thinking of which kind of algorithms is implementable on the device.
So do you mean the kind of platforms you can use them for, or do you mean how you can train these? The way of training, right? Okay, yeah. So they're black boxes. So every individual device needs some training. We are narrowing down. We can get them already a little bit more similar, so the amount of training is more limited, but still. So one way, and that's how we started, is with genetic algorithms. So evolutionary, just black box optimization. Which works, but it's timely, as was mentioned also earlier. There is also an archive paper where we use basically a perturbative way. So we call it homodyne gradient extraction. So this is a way to extract the gradient from a physical system by applying sinusoidal perturbations on these controls. And in this way, you can really do a gradient descent based on that. And in principle, you could even do that all in hardware. If you are really only interested in inference, then we have also shown that you can do off-chip learning. So you can make a surrogate model. So basically, a deep neural network that walks and talks like your device. You do your whole machinery of standard machine learning on that surrogate model, and then you transfer basically the weights, which in our case would be the controls, to the device. So that's a very similar approach as what most of the memoristive crossbar people use, right? For if they are interested in inference.
If I was not wrong, I have seen convolutional neural network implementation, or it was on other devices.
So we can also we can actually also do kernel operations, so CNNs also based on these RMPUs. That's in principle possible. We also have a work on that.
What about auditory application as well, which might, let's say, transformer could be, because it works with time series better, would be fit there better for auditory application, let's say.
Yeah, I agree. Yeah, thank you.
Thanks for the exciting talk. Really nice results and cool project. I was wondering, so when you come into these really beautiful looking, very small, very low energy, have all these nice reconfigurable things, there's so many benefits. Something I always wonder is when you then need to really interface it with all of the other machinery to make it work, things like amplifiers, buffers, all of that stuff. Do you think the particular RNPU, DNPU devices you use offer benefits there? Or for instance, if you were going to make something like a 3x3 MLP-esque architecture, would it need to be also 3x3 CMOS amps and buffers? And do you think it will play nice and allow you to keep that small footprint?
Yeah, this is a very good question. It was also alluded to earlier. At the end of the day, you have to look at the whole system, right? So we were in the recent paper that I discussed a little bit. We also forced by reviewers, okay, tell us really what is the overall structure, and you have to make estimates for the ADCs and everything. Do you need amplifiers and so on? So in this particular case, it turned out quite okay. But it's not like it's a given, right? You can probably make smart and less smart choices there, and that's, yeah, you need so much overhead and periphery in traditional CMOS that maybe it doesn't make sense to do this, and the same holds for the photonics part.
Yeah.
So that's why it's quite a.
It's hard, right?
Yeah.
Yeah, it's the kind of big next part of the challenge. Do you think you get something like N DNPs in a row before you need an amplifier, and maybe that can be optimized?
Right. So what you could, a way to save on periphery is that still in the analog you do a lot of condensation, right? So what you maybe you didn't see it, but we have like a 1 second soundbite, which we actually already downsample, which you really reduce the amount of data that you finally have to process than in digital. So there you can already make a lighter job and save energy downstream. Yeah.
Thank you very much.
Thank you.